The story of an asteroid that spins faster every year does not begin with violence, explosions, or dramatic collisions. It begins in silence. It begins in darkness. It begins in the vast, cold emptiness of the early solar system, an era long before Earth cooled, long before oceans formed, long before life took its first breath. In that ancient darkness, billions of small rocky fragments circled the newborn sun, drifting, colliding, merging, splitting, reshaping. Some became planets. Some became moons. Most remained what they were, wandering stones in a gravitational ballet that would continue for billions of years. Among these stones was a small, irregular object no larger than a mountain. It had no name, no identity, no orbit that mattered to anything alive. It was simply a leftover, a relic of materials that never found their way into a larger world. For ages it drifted quietly, turning slowly, its rotation set by collisions long forgotten. Nothing marked it as special. Nothing indicated that it would one day become the focus of global scientific attention. It was simply another survivor of cosmic creation. But over countless eons, something subtle began to happen. Something invisible. Something that even the most advanced ancient civilizations, had any existed, would never have noticed. As sunlight struck the asteroid's uneven surface, photons, the smallest measurable particles of light, bounced off its rocky exterior. Each photon carried momentum, and each time one of them hit the asteroid, it imparted a tiny push. The force was unimaginably small, far weaker than the pressure of a human breath. But over millions of years, these tiny pushes added up. The asteroid began to spin, slowly at first, then slightly faster, then faster still. Not by much, only fractions of milliseconds each year. But the increase was real, gradual, persistent, and unstoppable. Long before humans evolved or built telescopes, this lonely, anonymous stone was already changing, quietly responding to forces that almost defy imagination. It was being reshaped not by collisions or gravitational tides, but by sunlight, by the softest force in the universe. Had any observer been watching over geological time, they would have seen a transformation so slow it would appear motionless. But over the span of millions of years, the asteroid was gradually accelerating. And by the time humans developed the tools to measure such phenomena, this asteroid had become a scientific wonder, a rock spinning faster every year. For astronomers, discovering such an object was like watching a clock tick for the first time. They had always known that sunlight warmed asteroids, altered their surfaces, and contributed to their orbits. But they didn't fully understand how light could change an asteroid spin until they observed it happening. And when they finally traced the cause back to a subtle effect, now known as the Yarkovsky, O'Keefe, Radzievsky, Paddock effect, or YORP for short, they realized something extraordinary. Even the faintest forces can shape the cosmos. The asteroid's rotation rate was not constant. Each year, its day grew shorter by a tiny amount, mere fractions of a second. But over decades, centuries, and millennia, this change became measurable, and as astronomers studied it, they realized this acceleration was not random. It followed a predictable trend, driven entirely by the uneven way sunlight reflected off the asteroid's irregular surface. This discovery changed everything. It revealed that small bodies in the solar system were not static fossils. They were evolving, rotating, reshaping themselves. And the asteroid that spins faster every year became one of the clearest, most compelling examples of this cosmic evolution. But the story does not stop at acceleration. Because with every increase in spin, the asteroid edges closer to instability. Its surface begins to shift. Weak points stretch, cracks widen, boulders slide, and deep within its core, stresses build that could one day tear the entire structure apart. To understand this, scientists had to study its interior, the most mysterious part of any asteroid. Some asteroids are solid rock. Others are rubble piles held together by weak gravity. Some have porous interiors full of hidden voids. The structure determines everything: how fast it can spin before breaking, how it responds to sunlight, how it evolves over time. As astronomers examined the asteroid's light curves and radar reflections, they began to suspect that this particular body was not a solid monolith. It was likely a loosely bound rubble pile, a fragile assembly of stones that had survived billions of years of impacts. This made the accelerating spin even more significant, because rubble piles cannot withstand high rotational stress. They deform, they shed mass, and eventually they break apart. This raised urgent questions. How close was the asteroid to its breaking point? Was it already shedding dust or small fragments? Would it split into two pieces, as some asteroids have done? Or would it dissolve into a cloud of debris over thousands of years? Scientists began constructing models to predict its fate. Supercomputers simulated the asteroid's interior, revealing how stress would build as the spin increased. The results were sobering. If the acceleration continued at its current rate, the asteroid might reach its critical breakup threshold within geological timescales far shorter than previously thought. Not in millions of years, but thousands. Perhaps hundreds. Maybe even decades. Not long for a stone that has existed since the beginning of time. But the mystery deepened, because similar asteroids had already shown signs of rotational breakup. NASA's OSIRIS-REx mission discovered that Bennu, a near-Earth asteroid, was shedding particles from the surface. JAXA's Hayabusa 2 observed Ryugu's fractured, fragile structure, and radar observations of fast-spinning objects revealed that many were spinning close to the limit at which their loose material could no longer hold together. This meant the asteroid accelerating every year was not a rare anomaly. It was part of a broader pattern, one that might reshape our understanding of small bodies in the solar system. The more scientists studied these objects, the clearer the pattern became. Many asteroids spin at rates dangerously close to structural failure. Some have equatorial ridges formed by material migrating outward as rotation increases. Others have odd, pumpkin-like shapes caused by the redistribution of mass. A few have broken apart, forming binary systems where one fragment becomes the moon of the other. The asteroid at the center of this documentary may be on the same path. Its rotation is climbing. Its structure is under strain. Its surface shows signs of rearranging. And if the trend continues, the laws of physics leave only one possible outcome. It will eventually break apart. But long before that final breakup occurs, subtle changes will reveal its fate. Dust may lift from the surface as centrifugal force overcomes the weak gravity. Boulders may drift toward the equator. Small fragments may detach and enter temporary orbit. These signs serve as early warnings that astronomers are watching for now. To measure these changes, scientists track the asteroid's brightness pattern. As it rotates, different regions reflect light differently, creating a unique flashing signature. This pattern shifts as the rotation changes, offering precise data. Infrared telescopes reveal heat signatures, showing how sunlight warms and cools the surface. Radar reflects off the asteroid's shape, revealing its contours. Together, these tools create a detailed portrait of a world invisible to the naked eye, a world slowly reshaping itself under the influence of light. But the story grows larger still, because understanding a single rotating asteroid helps scientists predict the behavior of hundreds of others. Many near-Earth objects are small, irregular, and subject to the same YORP forces. Their evolution can change their orbits, bringing them closer to or farther from Earth. Even tiny shifts matter over long timescales. A slight increase in rotation can alter trajectory by millions of miles over centuries. This is why studying fast-spinning asteroids is not merely academic. It is a key part of planetary defense. If we can predict how an asteroid evolves, we can predict whether it will become a threat. If sunlight can alter its spin, it can alter its orbit. This knowledge is essential for safeguarding Earth from future impacts. Yet beyond the scientific and practical implications, There is something deeply philosophical about this asteroid story. It reminds us that the universe is shaped not only by grand events, but by subtle, delicate forces acting steadily over time. A faint push from sunlight can reshape a world. A whisper of radiation can alter destiny. The cosmos is not only violent, it is patient. And in that patience lies a beauty we are only beginning to understand. This asteroid's journey, from quiet relic to accelerating marvel, captures that beauty. It is the story of a small world sculpted by starlight, inching toward a fate written not by chance but by physics. A fate unfolding slowly, quietly, inevitably. As astronomers deepened their observations of the accelerating asteroid, they began running computer simulations designed to predict its rotational trajectory for the coming decades. What they found was astonishing. The asteroid spin rate was not simply increasing. It was increasing at an accelerating rate, showing signs of entering a stage known as spin instability, the point at which loose rubble begins to migrate outward from the body. If this continued unchecked, the asteroid could reach rotational breakup within a few centuries, or even decades, depending on where the internal stresses reach their thresholds. In many ways, this object offered scientists a cosmic laboratory for understanding the delicate balance between gravitational cohesion and rotational forces. Most asteroids are thought to be rubble piles, loosely held together fragments left from ancient collisions. These objects can rotate only so fast before their structural integrity collapses. However, some asteroids, rare ones, are monolithic, solid blocks of rock or metal that can tolerate extremely high spin rates. The primary challenge for researchers was determining which category this rapidly spinning asteroid belonged to, because the answer would dictate its destiny. To probe this mystery, astronomers used advanced radar mapping from Earth-based observatories. The radar beams that bounced off the asteroid revealed subtle variations in its surface texture and depth, indicating that it was not a uniform object. There were signs of porous regions, mixed densities, and ridges consistent with a body that had endured multiple impacts. This suggested that the asteroid was neither a perfect monolith nor a fragile rubble pile, but rather a hybrid structure, something stable enough to resist moderate spin increases, but vulnerable if rotational acceleration continued for too long. Next, researchers attempted to measure the internal temperature of the asteroid as accurately as possible. Heat plays a critical role in the YORP effect, as different materials absorb and emit heat with varying efficiencies. By studying the asteroid's thermal emission profile, scientists uncovered additional clues about its composition. The asteroid contained large patches of carbonaceous material, dark, heat-absorbing minerals capable of generating stronger YORP torques when sunlight strikes them. This was a breakthrough discovery because it revealed why this particular asteroid's rotation was accelerating so dramatically each year. With this information, scientists started reconstructing the asteroid's past. They estimated that millions of years ago, it may have spun much more slowly. Over time, as its orbit changed and sunlight struck it from new angles, the YORP effect began exerting stronger asymmetrical pressure on its surface. Gradually, over thousands upon thousands of years, the asteroid's spin rate increased until it reached its current pace, a rate so fast that even a slight increase beyond its tolerance threshold could send surface material flying into space. These projections raised a critical question. What would happen when the asteroid reached its rotational breaking point? There were two primary scenarios. In the first scenario, the asteroid could shed mass gradually, peeling off outer layers of dust, gravel, and small boulders that would drift into space and perhaps form a temporary ring around the object. This gradual shedding would act as a natural braking mechanism, slowing the asteroid's spin temporarily until it reached a new state of equilibrium. Several known asteroids have displayed similar behavior, creating spectacular dust tails that mimic comets even though their compositions are rocky rather than icy. The second scenario was far more violent. If the internal stresses grew too high, the asteroid could undergo catastrophic rotational fission. In such an event, the object would crack along its weakest axis, splitting into two or more fragments. These fragments, freed from the gravitational embrace of the original body, would drift apart and possibly form a binary or even a triple system, depending on their final trajectories. Some binary asteroids in the solar system are believed to have formed through exactly such a process. The rapidly spinning asteroid thus held the potential to become either a new source of cosmic debris or the birthplace of an entirely new miniature planetary system. This dual fate captivated astronomers and planetary scientists. The object became a case study in the delicate interplay between light, rotation, mass, and time, a balance that shapes countless bodies across the solar system. But while the science community debated models and scenarios, engineers and mission planners began considering the practical implications. If the asteroid was showing signs of structural instability, could it become a future threat to Earth? At its current distance and orbital configuration, the asteroid was not a danger. It traveled on a trajectory safely away from Earth, with no predicted intersections for centuries. However, if the asteroid fragmented due to rotational breakup, the resulting pieces could be nudged onto new paths. Even a small shift in trajectory over long periods could eventually create new risk factors. This possibility prompted some researchers to propose future monitoring or intervention missions. One idea involved deploying a spacecraft equipped with reflective materials designed to alter the asteroid's YORP effect. By strategically placing mirrors or panels on its surface, engineers could theoretically modulate the way sunlight heats the asteroid, slowing its rotation instead of accelerating it. While this concept remained theoretical and likely decades away from actual implementation, it demonstrated how seriously the scientific community treated the object's evolution. Another proposal suggested sending a lander to measure the asteroid's internal structure directly. Such a mission would provide unprecedented insight into how porous or cohesive the object truly was. Understanding these details would allow scientists to calculate the exact spin threshold at which the asteroid would break apart. This information could help determine whether an intervention mission was necessary, or whether natural processes would stabilize the object before a catastrophic breakup. But even as scientific interest grew, the asteroid itself continued its silent journey across the cosmos, spinning a little faster each year. Its increased rotation began to alter the distribution of dust and regolith on its surface. Loose material gradually migrated toward its equator, creating a bulging ridge. This phenomenon has been observed in several other fast-spinning asteroids, such as Bennu and Ryugu, where the redistribution of material forms a pronounced equatorial ridge resembling the rim of a spinning toy top. This ridge formation is a sign that the asteroid is approaching the point where centrifugal forces overwhelm local gravitational attraction. The faster it spins, the more material is pushed outward and upward, seeking the point where the forces reach balance. If the spin rate increases further, the ridge may become unstable, leading to slumping events where material avalanches off the surface and drifts into space. From the perspective of cosmic evolution, the asteroid was essentially reshaping itself in real time, one of the few astronomical processes unfolding quickly enough for humans to observe across the span of decades rather than millennia. Researchers marveled at this rare opportunity. With high-precision telescopes tracking its every motion, the asteroid served as a natural experiment in the physics of small bodies. As studies continued, the scientific community realized that this rapidly spinning object could also provide crucial insights into the origins of the solar system. Many fast-spinning asteroids are relics from ancient collisions, representing fragments of early protoplanets. By studying the rotational properties and internal composition of such objects, researchers could piece together the chaotic processes that shaped the early solar system billions of years ago. Every measurement added another piece to the puzzle, revealing how impacts, sunlight, and orbital evolution collectively sculpted the small bodies that now inhabit the asteroid belt. The story of the asteroid that spins faster every year was not just about rotation. It was about the constant, delicate interplay of cosmic forces. It was about how sunlight, the most gentle and universal force in the solar system, could reshape entire worlds over time. It was about the balance between creation and destruction, stability and chaos, inertia and acceleration. Yet perhaps most remarkably, the asteroid symbolized how even in the vast, seemingly unchanging darkness of space, nothing is ever truly still. Everything moves, shifts, evolves, and transforms. Even the smallest asteroid, no more significant than a mountain torn from an ancient world, participates in the grand cosmic dance. It responds to light, heat, momentum, and the invisible streams of gravitational influence flowing through the solar system. For astronomers, the accelerating asteroid was a reminder that the cosmos is not a frozen tableau, but a living, dynamic system. The more we observe, the more we learn that every object, no matter how small, holds the story of billions of years written in its motion and structure. And for a short period in human history, we are fortunate enough to witness that story unfold. As the years passed and the asteroid's rotation continued its steady acceleration, the scientific community began to focus more intently on the long-term implications. The object was becoming a beacon of inquiry for universities, space agencies, and researchers worldwide. Young scientists wrote dissertations on it. Veteran astronomers dedicated entire projects to understanding its evolution. Every new observation added urgency to a growing realization. This asteroid was evolving right before our eyes, and humanity had a rare window to study an active transformation in deep space. One of the great breakthroughs came when researchers developed more advanced thermal mapping techniques capable of detecting subtle heat fluctuations on the asteroid surface. These temperature maps revealed patterns far more complex than expected. Instead of a simple gradient between light and shadow, the asteroid displayed pulsating thermal zones that shifted as it rotated. These fluctuations suggested that the surface was composed of materials with wildly different thermal properties. Some areas cooled almost instantly when entering darkness, implying they were covered in fine, porous dust. Other regions retained heat for extended periods, revealing denser rock formations. A few patches exhibited unusual spikes of thermal retention that matched the signatures of metallic inclusions, small concentrations of iron or nickel buried beneath the surface. This new data refined the models of how the YORP effect was influencing the asteroid. Now scientists could calculate precisely which regions absorbed the most sunlight and which emitted the most heat. They discovered that even a small, asymmetric patch of darker material could significantly amplify the torque acting on the asteroid. These tiny imbalances, multiplied over millions of rotations, could explain the dramatic acceleration observed in modern measurements. This growing understanding led to a pivotal insight. The asteroid's acceleration was not simply a natural outcome of its shape and composition. It was also influenced by time. As micrometeorite impacts slowly altered its surface texture and redistributed dust, new patches of darker material were exposed while others were buried. These subtle changes in reflectivity caused the YORP effect to fluctuate over centuries, creating periods of faster acceleration and periods of slower spin increase. Humanity just happened to be observing the asteroid during one of its rapid acceleration phases. This realization cast the object in an even more fascinating light. Not only was it evolving due to forces we understood, but it was also evolving due to forces we had not yet fully considered, such as the long-term impact of surface aging, space weathering, and electrostatic dust migration. This meant that predicting its future was more complex than simply projecting its current spin rate forward. The asteroid was a living system in its own way, governed by a precise but shifting balance of light, heat, and material redistribution. To deepen the investigation, scientists turned their attention to how the asteroid's rapid spin affected dust behavior on its surface. In the microgravity environment of a small asteroid, dust particles do not behave like they do on Earth. Instead of adhering firmly to the ground, They could be easily lofted by electrostatic charging, caused by the interaction between solar radiation and the asteroid's surface. On a fast-rotating body, this charging becomes even more dynamic. Researchers theorize that the asteroid likely had an active dust environment, with grains continuously shifting, sliding, or even briefly floating above the surface before settling again. This dynamic redistribution further influenced the YORP effect, creating a feedback loop. Faster spin altered dust patterns. Dust migration exposed new materials. New materials affected thermal behavior, and altered thermal behavior accelerated the spin even more. This feedback loop hinted at the possibility that the asteroid was not simply on a path toward breakup, but on a path towards cyclic evolution, gaining and losing rotational speed depending on how its surface changed over time. It may spin faster for millennia, then stabilize, then spin up again, entering long rhythms dictated by processes so subtle they are nearly invisible to human observation. But whether this rotation would eventually stabilize remained uncertain. What was clear, however, was that the asteroid's spin was reshaping its surface dramatically. Over time, centrifugal forces caused fine dust to migrate toward the equator. Loose material gathered into a thickening ridge, reinforcing the equatorial bulge. As more mass collected there, the bulge grew wider and more pronounced. Eventually, the ridge became so steep that scientists predicted